Good morning. Hope all is well. I believe the grace of God is responsible for our life. We continue from where we left in our last lecture. Continue the methods of false position. We look at the bisection method in our previous lecture, which is also known as the interval halving method, where we halve the intervals until it's really small, which is taken as the root. But this is what we call the method of false position. The method of false position. This actually choose a particular iterative formula to find the root of the roots of a given function, and it is also of the view that the interval in which the root lies is given. The root lie is given. So this is the general iterative formula. This is a general iterative formula. So what we say is that you need to, or the points, that is, one is sk minus 1 is sk, or let's say sk minus 1 and sk. So sk here, sk minus 1, and when you have gotten their functional values, you just do direct substitution and you get the next the next iterative solution, which is always taken as the root, By looking at this, you see here, this is k minus 1, this is k minus 1, this is k, and when we start at k equal to 1, we can have a formula. So when k is equal to 1, we're going to have x naught here, we're going to have x1 here, x1 here, x naught here, x1, x naught, and this is giving us x2. So this is simplified here, as you see that given this interval, then the next root is computed as that. So it's the x value times the functional value of x1, the x1 value times the functional value of x0 over x1 minus x0, the functional values of x1 minus x0. And based on that, this formula, the other one we're using just a plus b over c, but this is a bit thick, but just a substitutive approach in finding the next approximation. This is a particular slope case, y over x case, a slope case. So the same condition applies here. If the next value is x2, that we said the next value is x2. I can illustrate this also for you to see. So watch it, as you can see here. This is x0 and this is our x1, that is the initial interval. So we compute x2 using the formula you see here, that is x2, that's the x2 formula to find that. But again, as we explained using the AB case, if x0 times x2 is less than 0, then the root will lie here. The root lies within this interval. Otherwise, that is when it's greater than 0, then the root will lie in this interval. So when it is less than 0, then the new interval becomes x0 and x2, as you can see here. And when it's greater than 0, the new interval will be x2 and x1, as you can see here. But for simplicity, we usually replace, when it is x0 and x2, replace the x2 with x1 so that we can use the same formula here. And when it is x2, x1, replace this x2 with x0 so that we can use the same formula as we have here. We do that to just simplify the computations for you. We do that computations for you. So the first one was a straight line case. This is a slope case. This is a curve graphically. This is a curve. This is a curve. So this is a slope. The first slope joining A and B. So this one is x1 and x2 rather. Then we can find x3, which will be by the formula we have there. That's somewhere here. We track the point here, up, down, down here, and we can join it by a new line. This is it. This is a new line, x4, where it cuts the x-axis. We track it down again, then we go like that again. We will keep going, we keep going until we come close to the point where the curve is really crossing the x-axis. We have explained that where the point crosses the x-axis is the root. So we were here, but based on this false position, we gradually keeps going until the difference between two solutions is less than a given threshold value or a given tolerance level. So that is a graphical representation of the method of false position. So this is a general formula. We can keep going to S3, X4, S5, but for simplicity, we keep changing with X1 and X2 so that you can easily understand the procedure. But the graphical aspect is showing from X1 to whatever we are going, but we are just repeating or using the X1, X2 case. You arrive at the same solution in both scenarios. The advantage here is also that the method will definitely converge and is faster than the bisection method, but can't also detect multiple routes as it was in the case of the bisection method. So it converges. Whatever you do, you are going to get a solution faster than the bisection, but cannot detect multiple routes, that being its disadvantage. We want to solve the same problem here as we solved in the bisection case using the method of false position. So we have the epsilon here. We could still stop after the 5th iteration and we take epsilon. It's not part of the question, but we can edit and have it in there. Then we have the initial interval here. So as you can see, I have fixed that as part of the question, otherwise stop after the 5th iteration. So solution iteration 1, we have to find x2 given the interval. So this is the interval. So this is x0, this is x1, x0, x1. So we have the general formula here from above. X2 is equal to that. We know x0, we know x1. We have to compute the f values, fx1 and fx0, given the function here. Those are the functional values, and we will definitely stop when this interval is less than 0. But from above, the functional values, when it's 0, we explain that in the bisect. When it's 0, we're going to get -3, and when it's 2, that is 4. That is 2, 4 minus 3, that is 5. That's 8 minus, that is 5. So f of 0 is that, f of 2 is that. Then we plug it into the function. Let me edit this place for you to see it clearly. Yeah, as you can see, f of x naught, that is a naught, is a 0 case that will give us -3, and f of x1 is the true case giving us 5. So we plug this value, and these values into this formula as you have here, and that is the substitution you can see here. We simplify and we get 0.75. The next thing is to check whether we can hold the iteration here, but this is the very first iteration and there's no previous value to compare with, so we may have to move on to the next iteration before we can make any comparison of such. So we didn't consider this stopping criterion at this point. This is the very first iteration and we did not consider that. But the next thing, or the next step, is to look for f of x naught times f of x2. We want to check whether it's less than 0. We want to check that. So we know f naught up there to be -3. Explain that, you can see here. So we have to check f of x2, this x2. We plug 0.75 into the question here and we find the corresponding value. So that is what we are seeing here, squared that, and we are getting minus that. So this times that is what we are seeing here, this times that, it's giving us a positive number, then that is greater than 0, a positive number, as you can see, a positive number. So if it's a positive number, that is a positive number. We computed this and that, and it's a positive number, which implies that the root rather lies in this particular interval, x2 and x1. Then we are saying, for simplicity, we can use x2 and x1 in our formula. So what we do here is say that our x2 here becomes our new x naught, and this becomes the new interval as with proper substitution. So this is the x2 becomes the new s naught for the next iteration. So 0.75 and 2 for the next iteration. So that is it. So check iteration 2. S naught is now that. In the previous case, S naught was 0, but S naught is that, X1 is that. We compute their functional values again, that is in the putting this and that in the formula or in the given problem. We have, this is for X naught and this is for X1, X naught and X1. Then we plug them into this formula, as you can see. We plug them into this formula, as you can see, simplify, and we have x2 as 0.9. At this point, we can make some comparison to check whether we can stop the iteration here, because this is a second iteration and there's a previous solution which gives room to make comparison. So the previous solution, that is the current solution, that is sk plus 1, this is something like x2 minus the previous solution, say s1. So this is current solution minus previous solution, current. So the current x2 value is what we have here, 0.9494. That's the current x2 value. Then we compare with the previous x2 value, 0.75. That's the previous x2 value. That is what we see here. And we check. That's the previous x2 value. Upon comparison, we realize that this value is not less than epsilon. Epsilon is 0.05 and 1.2 is greater than 0.05. So we may have to continue the iteration. So we find the functional values of f2 and f0 again. and you again seeing that is greater than 0, because this is negative, this is negative, this is negative, this is negative. So when we multiply, we're going to get something greater than 0, which means it will rather lie between x2 and x1, as I have explained. So we found x0, function of that, and it's greater than 0, then it's going to lie here. So which means this x2 is definitely going to be our x0, So x2, this is x2, 0.9494 here becomes the x0 for the next iteration. So the functional values again, as you can see, this is not, this is 1, this is not, this is 1, this is not, this is 1. And what happens is that we continue again. For x2, we substitute the respective values. This is fs0, this is fx1, x1, fx0, fx1 minus fs0. We simplify and we get 0.9. Then again, we have to check the stopping criteria. So the current solution for x2 is what we see here, 0.9894. But the previous solution is 0.9494. We do the subtraction and we are getting 0.04. And this value is less than epsilon, which is 0.05. And based on this condition, we can hold the procedure here, or the process here, because the stopping criterion is satisfied. So we are taking the final x2 value as the root of the given problem. So here, the root of the equation that you see here, equation s2 that lies within this interval, is 0.9894. This, by 3 iterations, we got our solution, compared to the bisection method where we use 5 iterations but still could not get a solution with a minimum error. So that is the method of false position that uses the slope case, but not a tangential slope. We look at the case where we are looking at a slope but a tangential slope. This, from the graph you will see here, this is not a tangential slope. This is just training these 2 points. You just bring down like that. That's a graphical or the geometric interpretation of the method of false position. You may have to try your hands on this particular problem. You want to solve that using the method of false position. So that is all for this section. Stay blessed and shalom. See you in the next lecture.